I will turn the floor over to Dr. Dorota Grezner-Brzezinska from the University of Wisconsin-Madison. No, yes, I said that right. I thought I said it backwards. Wisconsin-Madison, that's correct. She is the Satellite Division Chair and the organizer of this evening's plenary session.
All right, welcome everyone to a beautiful city of Baltimore, and welcome you to the best plenary session ever, I promise you. So, yeah, we have two phenomenal speakers today. One of them will take us all the way to the moon, and the other one will show us how to circumvent the globe. What can be more fascinating? Now, before I introduce our speakers, just a little bit of housekeeping. We ask both of our speakers to speak for 30-35 minutes, and then we have 10-15 minutes for Q&A after each talk. So please write your questions and then be ready when we open the floor for questions. So with that, with no any further ado, let me introduce our first speaker, Dr. Oskar Pozzobon, who is the president and CEO of Qascom. Dr. Pozzobon is a co-founder, president, and CEO of Qascom. He has been involved in the last 20 years in the design of all major European programs of satellite navigation, including Galileo and EGNOS, and has been a pioneer of GNSS security and authentication with more than 50 publications and 3 patents on this topic. He has been mission manager of several GNSS space missions, including the SCAN testbed on the ISS with ESA and NASA, sounding rockets with NASA and ASI, microsatellites experimentations with NASA, and the recent Lunar GNSS Receiver Experiment with NASA and ASI. So his topic for today would be Direction Moon, a journey of our satellite navigation satellite, a system beyond its limits. Please welcome Dr. Oskar Pozzobon. You can just leave it there for now. I'll leave you want me to hold it.
Thank you.
Thank you.
Thank you, Dorota, and good evening, ladies and gentlemen. It's a great pleasure for me for being here tonight. It's also a great pleasure to celebrate my 20th IRN GNSS. The first time I attended IRN GNSS was 2004. I was still a student, presenting work on GNSS authentication, guessed the faces of the audience in 2004, talking about security. And I spent half of my life, I'm 50 this year, I spent half of my life working on GNSS. And I had the great opportunity to work the last 4 years on a moon mission. So tonight, I will tell you the story, how it went, what we've been doing, and what we learned, and also what is my vision for the future of moon navigation. So our moon has a long history. Starting at 1610, back in the days, Galileo was doing the first experimentations with telescopes, trying to understand the moon. In 1651, Giovanni Battista Riccioli made the first map of the moon. I will show you later. It's very interesting to see that it's still valid today. A long history. The timeline there it's almost 400 years, and I don't go through everything, of course, but I guess to the recent launches to the moon have been very active the last 2-3 years. You have seen in the news, and really interesting to see that we had failures in the 70s, and we still do have failures in the last years. The moon, it's tough, it's challenging, and really didn't change the way we approach our mission, the difficulties that we have, and the challenges that we have to face. So Giovanni Riccioli, he was a geodesist from Bologna, and in 1651, he wrote this very interesting opera called The Majestum Novum, where he went through different types of analyses of in that period There were different theories. So the title really means new or majesto, old astronomy, embracing the new observances of others and the close ones. And it's impressive, the first page, where there is an engraved, an amazing design where two actors are showing, one is the observer, Argo pointing space and observing, and back in the days we could use only telescopes, so the plan was we observe and then we study, while Astrea is the other actor representing the science. And you see those plates, they represent the debate of that period. The plates on the bottom, it's really the abandoned concept of Earth-centric, while the two plates there are showing the balance and the ongoing debate on the heliocentric and the Earth heliocentric models. So we're still in 1651. They weren't really sure which model was correct, so just to give you an idea. America was 150 years old back at that time, and this was the work that the Italians were doing. And this is how we started our interest to the moon. So if you go through, you can find the entire scan of that opera. It's really interesting, and I would suggest you to do it. But you can go through, and you find the map. And the map of the moon of Riccioli with all the craters is still the map that we use today. The names are there, Mare Crisium, Mare Tranquillity. They are the names that were given back in 1651 and are still current. So that's really, really interesting to me. So, well, but how did we navigate to the moon before the navigation satellites? Well, take as an example the Apollo 11 mission. They had on board both the lander and the orbiter system called the Primary Guidance Navigation and Control System, PGNCS. The PGNCS was indeed supplied with a very accurate inertial measurements unit, but that itself wasn't enough. The IMU was drifting something like 0.05 degrees per hour, and the Apollo mission went up to 75 hours to get to the moon. That would have been 4 to 5 degrees of error, so they would have missed the moon pretty much. So they were integrating their measurements, the IMU measurements, with the telescope and the sextant, pretty much the same concept that we use with sailing and the boats. And the sextants were connected on the same frame of the IMU in a way that the sensors could tell the steering between a star and the other, and they were sending the measurements to the onboard computer. They were also getting measurements from the Deep Space Network and fusing all together. But just to give you an idea how precise this system was, Apollo 11, when they got to P63, the point that was just before the braking phase and then before the landing phase, the system started to measure the altitude from the radar, from the altimeter, and the computer, the onboard computer, was showing the discrepancy between the, let's say, the dead reckoning model and the real position with the one observed from the altimeter. And that resulted to be less than 1,000 feet, 300 meters, really, really excellent result considering we were in the 60s. So how can we navigate to the moon with GNSS? Well, we all know GNSS has been designed to work on our Earth. And back in the days when it was designed, it was even designed for mobile phones. So for sure, it wasn't designed for the moon. Well, if we use it in a LEO constellation, that's quite straightforward. The LEO constellation is below the satellite, so getting the signal is easy. But how do we get the signal from GNSS when we are beyond the MEO orbit? Well, we've been doing that for more than a decade, and the concept is to use, thanks to the design of the antenna pattern of the satellites, we do use two leaks of the signals, particularly the primary lobe and a secondary lobe. They do leak on a so-called off-board side angle, and they escape the Earth, and we can capture those signals beyond the MEO orbit. And it's normally used in geostationary satellites, but also NASA tested this concept, reaching a record with the MMS mission up to halfway to the moon. That's almost 30 radius Earth. So, well, we know we can use GNSS to the moon, but how hard it is and what are the challenges that we have to face? Well, first of all, the radiation environment. We all know deep space is tough, radiations, there's a number of effects that do affect the electronics and the devices. We are reaching solar cycle 25, so the radiation environment is challenging, and you have to consider that as all the deep space missions. The temperature environment is also challenging. The moon surface ranges from minus 180 to plus 140, something like that. And imagine an antenna that is facing the cold part and the warm part. This small thickness of the antenna has this unbelievable temperature range, so that's another challenge from a mechanical perspective. Receiver sensitivity. Everyone hears about indoor navigation. Well, when you go to the moon, that's an extra challenge. You need to capture the signal at 400,000 kilometers, and resivity is the key point to get and to being capable to get the signal. You need to integrate the signal for a longer time. That means also having accurate hardware, accurate clock. The moon is moving, and it's moving quite fast. Satellites are moving, so you can't simply integrate for 30 seconds the signal with a bad clock. So clock and timing, it's another challenge because, of course, we don't have space, we don't have power, and that's something you have to consider. The other aspect to consider is the knowledge of a dynamic model. You don't get always 8, 10, 12 satellites as we do have here. So you need to integrate to fuse your position, your measurements with some models. And that's kind of a mandatory when you are really, really far. And so you need to know integrate. You need to know the dynamics model. You need to integrate them with filters. That's something we don't normally do on Earth. I said time. Time is also important because not just for the signal processing part, but also we need time for the let's say for the sensor fusion part. We need time to know when we get assistance data, and assistance data is another point. The aiding data from Earth is another point that we need. It's really hard to extract the bits at 400,000 kilometers, so you need to consider when you are in a scenario where you get 2, 3 satellites only, very, very low C2 and 0, you need to get assistance from Earth for the ephemeris data, and that's require a communication channel. That's another challenge that you have to consider. Antenna design and the pointing requirement is also challenging. Antennas needs to be designed for the specific mission. If you are on a rover in the moon, if you are on a satellite, if you are a lander, you have different requirements. A satellite orbiting around the moon will have to track the satellite, so the design of an antenna will be different from a rover that could have a gimbal that points the Earth. So, and pointing is really challenging. You will see later, I will discuss that part as well. And finally, the landing. The landing itself, it's critical for the vehicle that is attempting the landing, but the engines have also the so-called plume effect. The plume effect creates lunar dust, and the lunar dust, the regolith contains metallic aluminum materials that they can get into contact with the surface of an antenna that can damage the communications and the ranging performances. So again, challenges, challenges, and challenges for the moon. So I've been involved in this mission, the Lunar GNSS Receiver, LuGRE. The LuGRE is a mission that was started in 2021 with NASA and ASI. The objective of LuGRE is to receive and process the signal at the moon, demonstrate navigation and time estimation, and support the development for future moon GNSS receiver. When we started 2021, I remember meeting with my colleagues. As usual, you have to go through a go, no-go decision, and everyone was negative. The roadmap, the timeline was super tight, super tough. Electronics team said, no go, we can't make it. The software team said, no go, we can make it. And of course, I said, let's do it. So we, in 1 year and a half, we built 3 releases of hardware: the engineering model, the engineering qualified model, and the flight model. They were developed in a year and a half, pretty much of time, because we are related to a lunar program called CLIPS. So there's not really time to wait. Either you take the train on that opportunity or you miss it. So development timing, it's also another challenge that we've been facing. And in the picture there, you see the 3 elements that have been developed. The black box is the receiver, the moon receiver. It's constructed with 2 hardware. They are 2 spaced receiver plus a supervisor board. The supervisor board is a radar device that is capable of switching in case of failure from a primary to a secondary device. It's also switching the RF cable. But it's also been designed in a strategy that if the supervisory board fails, it can pass through to the primary. So we can fail the primary, we can fail the secondary, and we can also fail, the supervisor can fail, and still we can talk directly to the receiver. This was one of the requirements we had in mind. We also designed the antenna you see there. It's a 9-element antenna, 14 dB gain, and that's installed in the lander, in the gimbal of the lander. And the idea is that the antenna is normally not deployed on the lander during the flight, and will deploy it once the lander lands and point Earth. So if we look at the mission profile, the idea is that Falcon 9 will launch the lander. It will be launched directly into the lunar transfer orbit. The vehicle will perform a number of moon transfer orbits around Earth, and we will have the opportunity to test the signal in different phases, in different distances. That will be done pretty much every day and in different parts. The vehicle will steer. The antenna, as I said, is not deployed, so we can point Earth, try to get a position fix, and then the vehicle will return in its natural position, which is the one where solar panel can capture the power. We can do 2 types of things. We can calculate the PVT, but we also design the system in order to capture the IF signals, and that's very interesting for the fact that we can do post-processing on Earth, but also for having signals for all future generations that we want to test IF signals at the moon surface. After a number of orbiting phases in the MTO, the lander will proceed straight to the moon, lunar phasing, braking phase, and will attempt landing into Mare Crisium. That's the final destination of our trip. So our journey, this is how you will see our journey when we are at 30 radius Earth distance. We are about 190,000 kilometers of distance. The signal power drops down. It doesn't drop down too much. As you know, path loss is logarithmic. But it's getting low, minus 150, minus 165 dBm, that's the range. We do get an average of 4 satellites at that distance with a max of 12. And we expect to calculate position with an error below 500 meters. The dilution of precision, you will understand, it's really bad when you're that far. We continue our journey, and we are at 45 RE distance. That's almost 300,000 kilometers. Signal power going down, minus 155 between minus 167 dBm. We still see an average of 4 satellites. Maximum number of satellites, it's dropping, and it's getting harder and harder. Position accuracy degrades, of course, for the dilution of precision. We are now at 60 radius Earth. That's pretty much the distance of Earth, 380,000 kilometers. Signal that can get as down as minus 170 dBm. We don't get from simulations all the 4 satellites. We've been running simulation with most of the times with 3 satellites. That means you require filtering and fusion with other techniques. Although there are some peaks of up to 6 satellites. Accuracy is really bad, below 1,000 meters of accuracy we expect. Of course, that's just estimations. And that's what you get when you are 60 RE. Then the lander will attempt the landing. That's a beautiful picture of Mare Crisium taken from one of the orbiters. And the landing will be still done with, of course, with the antenna closed. But once the lander is on the moon surface, the lander will try to deploy the antenna. And that's an interesting part. We have 1 degree of pointing accuracy requirement. Now, to give you an idea of what is 1 degree, it's the little circle there you see next to the Earth, while the 2 lines represents the orbital distance of 26,000 kilometers. That's the orbital distance. But we can't capture the satellites at 26,000 kilometers because they're pointing somewhere else. So pretty much all satellites that we can use, their primary lobes and secondary lobe are behind the Earth. So you will see them all around the border, the perimeter of the Earth. So pointing with 1 degree accuracy, it's challenging itself. But then it was surprising when we then discussed with all colleagues, including the lander company, where do we point the antenna? I mean, they have comms on board, X-band, S-band. So someone was saying, well, of course we point the antenna to the center of the Earth because the deep space network is there. And we were saying, no, we don't want that. We want to point the antenna towards the GNSS satellites because we need that. And this is the kind of things that you really discover when you work. And when you really get to that point, you don't discover them at SRR. You get to the point, and you have to make a decision whether you point antenna. That's another challenge that you have to face where you're on the moon. We do expect, however, better accuracy performances at the moon surface simply because we can continuously calculate position. We do average, so that's what we expect. So this is a video that's myself and my colleague James Miller. We were at the Firefly integration site. That's the lander. That's the antenna hat with the receiver you see on the table. The antenna hat has been used for testing in a, say, closed-loop environment with a simulator. And during that phase, the antenna was also installed, and that's the gimbal. The upper part, we have the GNSS antenna. The lower part, there will be X-band communications. The RF cable goes through the gimbal, and that's really critical because that will bend at minus 180 degrees of temperature. So the deployment of the antenna, it's really critical. Anything could go wrong during the deployment on the RF cable, for example. The receiver instead is installed on the bottom part of the top panel, just above the tank. So there have been 4 years of successful cooperations. The picture on the right is showing the AAV phase, and you see the receiver is installed on the bottom part. We have done so many meetings. I don't even remember all the meetings that we've done. Goddard, Kennedy, Italian Space Agency, Firefly, in Qascom, 4 years of traveling and testing and problems, and indeed it's been an amazing experience, this venture. This is the picture of the lander. It's completed, and it's currently undergoing TVAC testing at JPL and ready for the flight before the end of Christmas. So the navigation, we have GNSS and we are testing GNSS, but what do we expect? What can we expect in 15 years' time for the moon travels? We are working together with the European Space Agency on the Moonlight program. Moonlight will bring satellites, positioning and communication satellites to the moon. We are also working with the European Space Agency on a program called MOOD. It's a GNSS and LCNS simulator, so we will be capable to test all scenarios of missions and signals with both GNSS and LCNS. There are a number of constellations that are being built for the moon. Of course, we have Moonlight, we have LunaNet, we have the Japanese LNSS system. So I do foresee the opportunity in 15 years to travel, to have hybrid receivers that can track both GNSS and LCNS signals. And I foresee the possibility that a rocket can lift off from Earth with GNSS and can track GNSS signals all the way to the moon, and will start acquiring signals of the moon constellation as soon as it gets closer to the moon constellations, and use the moon constellations for the final landing in order to have high accurate and precise landing approach. Do I believe that we will not use anymore the Apollo 11 techniques? No. I think we will not be capable to use just GNSS or LCNS. There are other scenarios. The geopolitical situations is getting back to the Cold War, post-Cold War period. So cybersecurity, cyber attacks, jamming, spoofing, integrity failures are still all options that we will have to consider for the moon, exactly as we do consider today here for our Earth. And so I believe that still fusion between GNSS systems and inertial systems, orbital filters, star tracker will still be on the table even in 15 years' time. This is my, let's say, opinion. So, well, as a conclusion, I know there is a number of LuGRE member team here tonight with me. I would kindly ask you, to all of you, to stand up. And I think you're a great number. And I tell you, are much more. These colleagues are writing the history of moon missions, moon travels with GNSS. It's been amazing 4 years working with you, and I think what we're doing, it's incredible. We will leave for the next generation all pieces to build and for the future. So thank you very much, and enjoy ION. Thank you.
All right. Thank you so much, Oscar. A phenomenal presentation. I know that lots of us have lots of questions. So we are not going high-tech. There is no texting to read this year. We just go in and walk around with a microphone. So please raise your hand if you have a question for Oscar. I'm going to call on someone if there is no volunteers. Alison Keeley, where are you?
Okay, so thanks very much for the presentation. We work together, as you know. We are developing also the GNSS receiver on Lunar Pathfinder, so I know well the MMS. One question I have, today in your receiver, you were saying the number of satellites we are losing while the distance is increasing. Obviously, this is related to the pointing of the antenna, the gain of the antenna, and also the sensitivity of the receiver, no? The high sensitivity of the receiver, and what is the threshold. And I was wondering, what is the figure, what is the threshold you're able to track and to acquire GPS and Galileo satellites?
The figure?
Yeah, in dBs Earth, the signal.
So first of all, something I didn't mention is that I think we have a total of 40, 50 people working in this team, and everyone is expert of something, from the signal processing, PVT, sensor fusion, and mechanics, AAV. So I will try all my best to give you answers for this. So, for example, this is a question I don't know anyway. But
as a reference,
the simple answer is up to 4 satellites we can attempt positioning, and of course we do get from the aiding from Earth ephemeris data, so we could use 2 GPS and 2 Galileo satellites. That's foreseen in the Galileo design. Thank you, Galileo, for that. When you go below 4 and you have 3, we have to do the sensor fusion with the orbital filters. I think that's a very generic question. Now, getting into the details, I think even here tonight you get...
It's an important figure, but anyway, congratulations. And the other question was obviously when the antenna is folded, and I finish with that, obviously this has an impact on the gain and also the multipath effects. Is this something well modeled, or is very difficult to model?
Well, so when the antenna is closed, the vehicle has to steer, because of course the antenna, active antenna part is pointing up. I probably don't expect too much multipath in the travel, in the cislunar transfer, because there is nothing around except the lander itself. We might get multipath from the Earth surface if the weak signal can bounce. That would be part of the experimentation. It would be very interesting to see if we do. When we worked with the ISS, no one would have expected multipath on the ISS, and the solar panel were bouncing signals everywhere. So thanks to this type of experimentations, you learn, you gain, and for the future, you know how to mitigate it. Yeah.
Excellent. Okay, congratulations for that.
Thank you.
Thank you.
Thank you for the nice presentation. I truly enjoyed it. So my question is for the, to high sensitivity receivers, I assume you need to correlate over a longer period of time so that you have that correlation gain. So my question is, how much latency do you experience by having this long correlation window?
Latency?
Yeah, because, you have to wait for a while, right?
Well, for sure, at least the integration time. So if you integrate 30 seconds, and then it's going to be milliseconds to calculate the position. But I don't know the figure exactly. The receiver can be configured in a number of options. So the latency, the immediate answer that I can think of is that is at least the minimum integration time plus the time to compute the PVT. I have colleagues in the room that will give you exactly the milliseconds that are required. So if you meet me after, they will tell you the exact answer.
Yeah, thank you for the great talk. I think you've talked about the positioning accuracy you can get at different altitudes. Can I ask about the timing accuracy you're kind of expecting for these
I
orbits?
think if I remember, the simulations are in the order of microseconds, so you don't reach the nanoseconds. And again, of course, it's part of the dilution of precision. But they are all guesses from simulations. We will have to see the real results to understand. Also, you probably remember I mentioned the clock. We didn't redesign the hardware from scratch. There wasn't the time. We did it in 1.5 years, so we were stick with the clocks that we had on board, and they also impact the timing performances. Ideal world, you will want a CSAC together with the OCXO, and that's the ideal world, but there wasn't time, there wasn't budget, there wasn't space, there wasn't power, and that's why we love the moon missions.
I see. Thank you. If I can ask one more question, are you considering like the relativistic effects, like when we like do time transfer, like?
I think they're considered in the filters, in the dynamic models. For sure, gravity is considered, pressure from radiations, yeah. But that's another specific thing.
Oh, yeah.
That, of course.
A very specific thing. Yeah, thank you very much.
You're welcome. As a plenary, I was expecting a very generic question. Instead, you're...
So Oscar, I'm going to ask very generic questions, and it may indicate that I haven't been paying enough attention, but I just want to ask, so you fly to the moon and everything stays there, or there is any plan to retrieve it back?
Excuse me, if I fly to the moon?
You just fly to the moon, the lander is landing, and you just leave everything there, or there is a transport back?
Yeah, so no, it's not coming back, and it's actually quite unlikely that we'll survive the moon night. So lifetime is expected 2 weeks.
Okay.
The battery is not designed, and most of the missions, unfortunately, that's another challenge for the moon, surviving the night. It's 2 weeks, super cold temperatures, and yeah. This was a simple question. So. I shouldn't say that I've been 20 years of ION doing technical presentations.
Thank you so much for the presentation. About your GNSS antenna, what was the gain of it, and how wide was the main lobe?
So the antenna, what was the?
Do you know what was the gain, and how wide was the main lobe?
So the gain is 14 dB. I don't remember the figure of the half-power beam width. Maybe some of my colleagues from NASA, they remember half-power beam width. 6? 6. See,
Thank you.
they're helpful.
Thank you.
If we wait 5 minutes, they will ask me about security and jamming of the moon receiver, I'm sure.
Thank you very much for a very enjoyable presentation. I have a very short question. I was wondering, what is the expected time span for the lunar satellites before it comes crashing down on the moon?
The time?
The expected time span of the satellite. For the GNSS satellites, it has a lifespan of about 12 years before it comes crashing down, isn't it? What is the time span for the lunar satellites?
So if I understood, you mean the time of the mission?
The total number of years that it will circulate the moon.
So the mission will last 40 days of travel, and 2 weeks on the moon surface.
Yeah. But of course, the satellites will not be.
This is for LuGRE.
For Lunar, yeah.
Yeah, for Moonlight and other constellation, of course, is different.
Yeah. My question is, how long will it take for it to become unoperational?
I'm sorry, how long it will take to become?
Unoperational.
Operational?
Stop operating. It will stop. Sorry about I prefer English. The satellite will definitely come crashing down to the moon, isn't it? One day.
The lander?
Yeah.
Yeah. So the LuGRE mission foresees 40 days of travel to the moon. The lander will land to the moon. there's 2 weeks of operations during the day of the moon. The entire life cycle of the moon is 28, 29 days, and it will die during the moon night, and that will be the end of life of that mission. They will try to wake it up after 2 weeks of night, but it's unlikely it will work.
All right. Okay, thank you very much.
I hope I answered your questions. If you have questions related to the moon constellations, I would suggest to ask them to the NASA or ESA colleagues. They will give you all the lifetime related to that.
Thank you very much.
You're welcome.
Thanks, Oscar. Dorota's making me ask a question, so apologies in advance for this. This is really exciting, and I just want to find out how I can get involved in your team. But other than that, do you have any comments about reference frames? Is there any consideration to the stability of reference frames, given the lunar constellations and the GNSS constellations and the fusing of the data from both of those? Are they the same reference frame? Do we have different timing reference frames for the moon versus what we currently have? And how are these issues being addressed?
Okay, very interesting question. Of course, also very technical. So I'm pretty sure we're using the Earth reference frame. They're doing yes. And as well, timing. Of course, the timing that the GNSS receiver will calculate is the GST time, the system time. And there are lots of very interesting discussion going on with the time at the moon. And should we use the time at the moon? The time at the moon will be different of the time at Earth for the different gravity and speed. And one of the interests we have in using GNSS at the moon is the potential to have time transfer for operations. So regardless what would be the final decision on time at the moon or time on Earth, but having a GNSS receiver at the moon, one of the advantages would be also to have UTC and Galileo and GPS time transfer. You're welcome.
Exciting project, obviously, and congratulations to all the team. One thing that struck me is that, fundamental of GPS, as soon as we start looking at this, is we're taught that you need a well-distributed transmitter, the dilution of precision and the DOPS to get an accurate position. To me, it seems like you almost have a one-point source for your transmitters, which would be, what's the calculation of your DOPS, and how do you get to that kind of level of precision at that distance when you literally have one point source for your transmitter?
Yeah, it's correct. That's why the accuracy in both positioning and timing is very low. The main objective of this mission was experiment to see if we can capture the signals. So we all knew we weren't getting accurate position in timing, but the point is, can we get the signals at the moon for the future? In the answer before, I just mentioned one of the possibilities, which is time transfer. No one thinks that we're going to send an astronaut with a huge antenna on the backpack to track the signals at Earth, of course. So the objective of the mission is experimentations, understanding can we get the signals there, and also we are preparing for the future constellations, lunar constellations. So no expectations on precision and time accuracy so far.
Will any of the data be made public throughout the lifetime of the project for research purpose or not?
I'm sorry, because the speakers are pointing there, and it's really challenging to understand.
Will any of the data be made public for research purpose at a certain point in the project?
Yes, so one of the objectives of the mission is also the dissemination and results, performances, and as well, I believe the IQ files will be released and to the public, sure.
All right, I'm sorry to close the questions session of questions for Oscar, but Oscar is not disappearing. He has also a number of colleagues with him, so please continue this fantastic conversation. We need to move on to the next talk. Thank you so much. Please give me one round of applause.